Okay, so in part 1 we learned that all objects emit electromagnetic radiation. Cold object will emit wave with low frequency, while hot object will emit wave with higher frequency. Okay, now, so let's look at this. Okay, again, we look at this, the oven heating element. So when the object temperature is higher, then the frequency of oscillation of this particle will be higher. So that means the electromagnetic radiation that is emitted will be at a higher frequency. So when the frequency go into the frequency of visible light, then we will be able to see that the object will start to glow. Okay, start to glow and emit visible light. Okay, emit light. Okay, now, so by logically, scientists in classical physics, in classical physics, the logic is that if the reason why it can oscillate at higher frequency is because it has more energy, right now. Okay, more energy, so it can oscillate faster. So logically, if the particle oscillate at higher energy, okay, this particle oscillate at a higher frequency, so logically the energy, the energy that is emitted, the energy that is emitted should also be higher, right? Should have more energy. So from this logic, from this theory, from this concept, they get a graph. That means the relationship. The relationship between the intensity, the radiation intensity, the relationship between radiation intensity and wavelength, and wavelength should be that if the wavelength is longer, longer wavelength, that means the frequency is low. So that means the intensity, that means the amount of energy that is emitted in in long wavelength should be low. And as the wavelength gets shorter, that means the frequency increase. Frequency increase. This one, frequency is low. If the wavelength is long, then the frequency is low. If the wavelength is short, then the frequency will be higher. So by right, it should be like this. That means as the frequency getting higher and higher, then the intensity of the radiation should increase higher and higher and higher. So this is the relationship that they get from this logic, from this concept, from this concept, this is the relationship. Is it that they should get between radiation intensity and wavelength? So as a wavelength gets shorter, then the frequency increase, then the radiation intensity should be higher. So for example, this oven heating element. Okay, for example, this heating element. Okay, for example, this heating element. The reason why this heating element glow, okay, we can see that it glow red in color is because the intensity, okay, the radiation intensity of the frequency, okay, of the frequency that is in red light, okay, red color light is high a lot. That means a lot of energy go to frequency that is in the frequency of the red light. So we see that is a glow red color. And all the other frequency, the longer frequency have less amount of energy. Okay, have less amount of energy. So that means that if we detect the radiation that is produced from this heating element, okay, the radiation that is released from this heating element, we will find that the long wavelength, the energy is very low. That means total energy from electromagnetic wave with longer wavelength is lower, while total energy from shorter wavelength is higher. Okay, get the idea? Okay, that means a lot of the electromagnetic radiation that come out, okay, or the majority of the electromagnetic radiation that is produced by this heating element, majority of the energy go to electromagnetic wave with higher frequency. Okay, when I say higher frequency, I mean in like the red light, orange color light, and yellow light. Okay. Okay. For example, refer to this diagram. Okay. For example, refer to this diagram. The reason why this heating element glow red in color is because a lot of the energy is here. Okay. A lot of the energy is in this region. Okay, in this region, majority of the energy is in this region, and other region like infrared radiation, microwave, radio wave is less lah. Okay, less energy in wavelength of longer wavelength. Infrared radiation, microwave, radio wave is less. Okay. More energy go towards the wavelength that is within the visible light, but in the range of red to yellow color. Okay, you don't see that this heating element become like there's green color or blue color or purple color because there is no energy or very little amount of energy that is within the very little amount of energy that go to electromagnetic wave that has the wavelength of green color light, blue color light, or purple color light. Okay, very little energy go to that frequency. Okay, majority is inside the red to yellow color. Okay. Like that. So that is why it have this kind of color lah. Okay, the heating element is like that. So from this part, this looks like correct lah. This graph looks like correct. That means the wavelength shorter. That means frequency higher. Then the radiation intensity will be higher. Okay, that means the electromagnetic radiation that have higher frequency, it will be able to release more energy. Okay, so it looks logical lah. It looks like correct. However, when the scientists investigate and detect Okay, they investigate the actual spectrum of radiation that emit by very hot object. Okay, emit by very hot object. Very hot object, for example, this bulb. Okay, for example, this bulb. Okay, we compare these two bulbs. This bulb have the temperature of this bulb will be lower lah. This bulb have a higher temperature compared to the bulb on the left. The bulb on the right have higher temperature. So when they compare the radiation that is emitted by these two, what they find that when the temperature is lower, yes, the graph looks like it follows the theory. Okay. The graph looks like it follows the theory. But what they find is when the temperature of the object is higher, okay, when the temperature is higher, they find that, okay, yes, the energy go up. Okay, the energy or the intensity of the radiation go up when the frequency decrease. But when the frequency go until a certain threshold, okay, over a certain number of frequency, that means when it go near to the ultraviolet frequency, okay, when it go near to the ultraviolet frequency, they find that the energy drop drastically. Okay, they find that the energy decrease. Okay, what does this mean is that, okay, let's say this is the here to here, this is the frequency for ultraviolet lah. Okay, our wavelength of ultraviolet. Okay, so let's say here to here is the visible light. Visible light. Here to here is the infrared. Here to here is microwave. Here to here is radio wave, for example lah. Okay, for example. So what they find is that when the frequency become higher and higher and higher, okay, and the energy, okay, the intensity of the light, the intensity of the electromagnetic wave that is produced, which is at higher frequency, the energy, the total amount of energy drop when it go towards ultraviolet. Okay, when it go towards the ultraviolet frequency and beyond, and higher frequency than that, they find that the total energy that is released is less. Okay, lower compared to energy that is released from lower frequency. So that means this actual reading, this actual reading from reality, real life situation, it doesn't match with the theory. The theory says that frequency increase, then the energy that is released should be also higher. Okay, you should get more energy that is in the higher frequency. But in reality, that is not the case. In reality, even though the temperature increased until very, very, very high, but the amount of energy that is in the very high frequency, that means ultraviolet and above, will be very low. Okay, it will drop very fast. Okay, so why like that? So the scientists at the time, during the classical physics era, during the time of classical physics, they cannot explain. Okay, there are a lot of theory lah. Okay, they throw around a lot of theory. Maybe there's something wrong with the reading or something, and many people repeat the experiment and so on, but they cannot explain. So until one day, there is one German physicist lah. Okay, there's one German physicist that recommend to the scientific community. Okay, he recommend his idea is that let's study this phenomena with an ideal object. Okay, let's study this phenomena with an ideal object, because a lot of people think that the reason why the energy drop is due to error or like natural error. That means due to imperfection of the heating element and so on. There's a lot of other issue lah. Okay, a lot of other variable that people think that maybe is the one that cause this graph. Okay, that produce this graph. A lot of people have a lot of different idea lah. Okay, what is it that caused the graph to be like this instead of like this? Okay, so the German physicist he give a suggestion lah. Okay, let's pretend that there is an object. Okay, let's pretend that there is an object which is a perfect absorber of radiation and also a perfect emitter of radiation. That means, let's say that we have an object. Okay, let's say that we have an object that it will be able to absorb all electromagnetic radiation. Okay, electromagnetic radiation. That means don't care radio wave or microwave or visible light, infrared, ultraviolet, X-ray and so on, no matter what. Okay, electromagnetic radiation fall on this object, the object will be able to absorb all of the energy from the electromagnetic radiation. That means all will be absorbed. That means zero, none of it will be reflected. Okay, no reflection. Okay, the electromagnetic radiation is not reflected. Okay, so what happens if the object does not reflect electromagnetic radiation? Then the object will be black, right or not? You think why is it that the object will be black color? Just think of how is it that we can see things. We can see the table. Why is it that we can see the table? Because light fall on the table, reflect and go into our eyes, so we can see the table, right now. But if you imagine that if the table, what will happen if the table absorb all of the light energy that fall on the table? That means no light reflect from the table. If the table do not reflect any light, then you cannot see the table lah, or you will see the table as black color. Okay, you see the table as black color. So because like that, because the object will look like black color, so they call this object a black body. Okay, they call this object a black body lah. So this black body is a object, an ideal object that can absorb all electromagnetic radiation. It absorbs them perfectly. Okay, none of it will be reflected. Okay, and after the energy from the electromagnetic radiation is absorbed, it will be converted into thermal energy. That means it will be converted into heat energy and cause the object temperature to increase. Okay, cause the temperature of the object will increase. So when the temperature of the object increase, the particle inside this black body will oscillate, and the energy that absorbed just now will be re-emitted Okay, it will be emitted out, okay, as electromagnetic radiation. So we say that this object, this black body object, is a perfect absorber of radiation, okay, electromagnetic radiation, and also able to is a perfect emitter, okay, perfect emitter of radiation, okay, electromagnetic radiation. So this is what we call a black body lah. Okay, why is it that they want to use this black body? They want to suggest this black body to study. Okay, to study this black body, because just now in reality, if you want to study object that is in reality, there will be a lot of variable. Okay, a lot of variable involved. So it will make it very difficult to focus on what is it that caused this graph to appear. Okay, what is it that caused this graph to appear? So he suggests this black body, and people will study what will happen to the electromagnetic radiation that is emitted if we have a perfect object that is if we have an ideal object that is a perfect absorber of electromagnetic radiation and also a perfect emitter of electromagnetic radiation. Okay? Okay, so we look at here, it says that a black body is an idealized body that is able to absorb all electromagnetic radiation that fall on it. A black body can also emit thermal radiation, depend on its temperature. The radiation emitted form a continuous spectrum and is unaffected by the nature of the black body surface. Okay, thus, an object emitting electromagnetic radiation, which is determined by its temperature, is known as a black body radiator. Okay, so basically what it means is, you see at the first part here, it says a black body is an idealized body that is able to absorb all electromagnetic radiation that fall on it. So, that is what we say just now. It is a perfect absorber. Okay, a black body is a perfect absorber of electromagnetic radiation. And we say that, and then after that, we say a black body can also emit thermal radiation, depend on its temperature. That means that just now we say that it absorbs all the electromagnetic radiation, right? So all of this electromagnetic radiation will be converted into thermal energy. Okay, thermal energy. That means it makes the kinetic energy of the particle increase and increase the temperature. Okay, increase temperature of the object. And when the temperature is higher, then it will be able to emit, emit the electromagnetic radiation, depend on its temperature. That means if the temperature is low, then it will emit radiation that is at a lower frequency. If the temperature is higher, then it will emit the radiation at a higher frequency. Okay, like that. So that is what it means when we say a black body can also emit thermal radiation. It's called thermal radiation because the radiation that is emitted depend on its temperature. Okay, depend on the kinetic energy of the particle inside the object. Okay, higher temperature oscillate faster than higher frequency. Okay, like that. Okay, so it says that the radiation emitted form a continuous spectrum. It says that it is a continuous spectrum because it means that the radiation that is emitted is in all frequency and all wavelength. Every wavelength also got, every frequency also got. Okay, and unaffected by nature of the black body surface. That means the surface, you don't have to think about is the surface rough or shiny or whatever. Okay, no. We want to limit the variable as much as possible. You don't have to worry about what is the nature of the surface. Okay. So an object emitting electromagnetic radiation, which is determined by its temperature, is known as a black body radiator. So for example, just now we have the bulb. So this bulb is considered as a black body radiator. Okay, this bulb is considered as a black body radiator because the higher temperature, the higher frequency of electromagnetic wave that it can emit. If the temperature lower, then it will emit the electromagnetic wave at a lower frequency. Okay, get the idea. Okay, so a black body radiator can be anything basically. Okay, anything can be a black body radiator. The table, our body, your pencil box, your pen, whatever, everything can be a black body radiator because everything also emit electromagnetic wave, right now. Everything emit electromagnetic radiation. So everything can be a black body radiator. Okay, depend on the temperature. Alright. So one thing that I want to point out is there is no such thing as a black body. Okay, this black body is a idealized body. Okay, idealized body. That means in real life there is no black body. Okay, there is no black body in real life, but we have object that is near, that it have a characteristic that is almost like a black body. Okay, almost like a black body, but you don't have like a perfect object that is exactly like a black body. You don't have. Okay. So, for example, okay, what is it that we can say that is like a black body? So, for example, this ear cavity Okay, ear cavity. We say that the ear cavity is like a black body. Why? Because you say, okay, the ray of light that enter the ear cavity will undergo repeated reflection on the inner wall of the ear cavity. At each reflection, part of the ray are absorbed by the inner wall of the ear until all the rays are absorbed. Thus, the ear cavity act like a black body. So, you see, every time there is reflection, let's say there is a radiation that go into the ear cavity. Okay, radiation that go in, it will reflect inside the ear cavity. Reflect. So, every time it reflects, a little bit of the energy will be absorbed by the wall of the ear cavity. So until the end, all of the energy is absorbed by the ear cavity. So no radiation come out no radiation is reflected out from the ear cavity. However, okay, that is why the ear cavity looks dark. Okay, when you look inside the ear cavity, you cannot see anything. It's dark because all the light that go in, the energy is absorbed by the ear cavity. Okay, no light reflect out. Okay, no light reflect out, so it looks dark inside. Okay, so however, when you use a radiation detector. Okay, when you use a radiation detector to detect whether the radiation come out or not, you can detect radiation that come out, right or not? Because inside the ear cavity is warm, okay, higher temperature. The temperature is higher, so that means this ear cavity emit radiation. okay, emit radiation. So we take it that the radiation that is emitted by the ear cavity come from the energy that is absorbed just now. Absorb energy and then release back the energy as thermal radiation. So we say that the ear cavity is like a black body lah. But of course, I want to stress that there is no actual black body. Okay. Okay. So if you look at this. If you look at this diagram, okay, you look at this picture, it says that at the bottom here, it says photograph 7.1, example of black body in daily life. I believe this statement is wrong, okay? I believe this statement is wrong. Is like what I say, there is no black body, actual black body in real life. But what is it can say is that these are example of black body radiator. If this is example of black body radiator, then this is correct lah. Okay, example of black body radiator in daily life. But all of these things, black body? No. Okay, they are not black body. The car is not a black body. Okay, the heating element is not a black body. The filament of the bulb is not a black body. Why? Because does it look black or not? First of all, the car. Okay, the car, yes, it got emit thermal radiation, it got emit radiation. So the car is a black body radiator, but do the car absorb all of the light that fall on the car? When you look at the car, you can see the car because of what? Because of light that reflect from the body of the car, right? Okay, the light that you see coming from the car is not produced by the car itself, but is due to reflection. Okay, due to reflection of light that fall on the body of the car. So that is why you can see the car. So since the car can reflect light and reflect a lot of light, so you cannot say that the car is a black body lah. Okay, it's not black body. If it's a black body, then no light should be reflected from its surface. All of the light, all of the electromagnetic radiation should be absorbed. Okay, you see or not? Okay, so the oven heating element also you cannot say that is a black body, because some of the light that you see is include the light that is reflected from the heating element. Okay, that means not all of the light is come from the thermal energy. Okay, from the heating element. Some of them is due to reflection. Okay, get the idea? Okay, so after studying the black body, okay, using the black body as an example to study, okay, our main character lah, okay, the person that think of the idea of quantum, okay, quantum theory is Max Planck. Okay, Max Planck. Okay, you don't have to worry about his when he lived from what year to what year. No need to worry lah. Okay, no question going to ask you about his how old is he or what year he died or something like that. Okay. Okay, so Max Planck is the one that think of the idea, that think of the concept of quantum. Okay, think of the concept of quantum. That means where it means that the energy is actually discrete. Okay, energy is actually transferred in a discrete amount. Okay, so what does it mean by discrete? Okay, so we see we compare discrete and continuous. Okay, we look at continuous. If continuous, that means 1, 2, 3. Between 1 and 2, you have 1.5. Between 1.5 and 2, you have 1.75. Between 1.75 and 2, you have 1.7525. Between 1.7525 and 2, you have 1.75255, for example. So that means you can continuously divide into smaller and smaller amount. Okay, that is continuous. You can infinitely, you can continue to divide it into smaller amount and smaller amount and smaller amount infinitely. Then that is what we call continuous. That means there is no gap. Okay, it continuous. Okay, discrete is either 1, 2, or 3. There is no in between. Okay, there is 1, 2, or 3. There is no in between. So what Max Planck is suggesting is that what his idea is, he thinks that okay, if energy is transferred in discrete amount, that means, for example, let's say the energy can only be transferred in 1 joule. Okay, only can be transferred in 1 joule at a time. That means every time you transfer energy, it will plus 1 joule. 1 joule transfer, it will increase by 1 joule. 1 joule transfer, increase by 1 joule. So that means you don't have to increase 1 joule, slowly transfer 0.1 joule and then 0.1 joule. So the energy slowly increase, like 0.1 joule, 0.2 joule, 0.3 joule, 0.4, and then 1 joule. 1 joule and 1.1 joule, 1.2 joule, like that. Slowly increase, no. Okay, what his idea of the energy being discrete is that energy transfer in a fixed amount. Okay, every time an amount of energy is transferred, it will be transferred in a specific amount. Okay, 1 joule, 1 joule, 1 joule, 1 joule, and then transfer. Okay, it will not transfer like a little bit. Okay, sometimes a lot, sometimes a little bit. No, don't have. Transfer in energy is transferred in discrete amount. Okay, 1 joule, 1 joule, 1 joule, 1 joule. For example, 1 joule. Okay. Okay, so that is his idea. Actually, he is also at the beginning. He is also not sure. Okay, Max Planck is also not sure about his idea. But from what he see, the only way to explain this shape of the graph, the only way to explain the graph is this shape. Okay, like a bell shape, is because the energy is discrete. Okay, there's two main points here. Okay, Max Planck, there's two main points in Max Planck's idea. Okay, first is energy is discrete. Okay, and the second is that the energy is limited. Okay, energy is not unlimited, it's limited. Okay, so let's say that, for example, this black body, if this black body absorbs 100 joule of electromagnetic radiation, then it can only emit 100 joule of electromagnetic radiation. This electromagnetic radiation that come out maximum is only 100 joule. It is impossible for it to emit 101 joule while it only absorbs 100 joule. Where do the extra 1 joule come from? This is not logical, right now. Okay, not logical. This is also one of the problem for this graph. Okay, this is also one of the problem for this graph, because this graph shows that when a wavelength is long, okay, frequency low. Okay, when the wavelength is long, frequency low, and when the wavelength is short, the frequency is high. You see that the amount of energy that is emitted is getting higher and higher exponentially. That means it goes towards infinity. You see or not? That means if the frequency is very high, then that means the energy that is emitted will be infinitely high. So this will be not logical because the energy that is transferred is limited, right now. How is it that if you give an object a certain amount of energy, but the object can emit an infinite amount of energy? This is not logical, right now. For example, let's say the heating element of the bulb, okay, the heating element of the bulb. The electrical energy that you supply to the bulb is 100 joule, okay, 100 joule for example. So it is not logical for the bulb to be able to emit energy that is super high, infinitely high at the very high frequency. When the frequency is very high, when the temperature is very high, the amount of energy is the amount of energy that is emitted is infinitely high. This is not logical, okay, impossible. So if you supply with 100 joule, then the bulb should also be able to emit maximum 100 joule only lah. Okay, right. So that means this graph, this concept from classical physics is not logical. Okay, not logical. Okay, so Max Planck's idea is energy is discrete, energy is limited. This is very important because only when energy is limited and energy is discrete that you can get the graph that look like a bell shape. Okay, so you imagine, let's imagine like this lah. Let's say that you have okay, so this is wavelength. This is the radiation intensity. Okay, so let's say that I draw particle, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, let's say this 10 particle represent, this 10 circle represent the particle that oscillate at different frequency. Okay, so with here is at the lower frequency because longer wavelength, lower frequency, and over here is where the frequency is very high lah. Okay, when the frequency is very high. So in order for the particle to oscillate at low frequency, okay, the particle don't need a lot of energy, right? Okay, if it oscillate at low frequency, that means oscillate very slowly. Logically, it doesn't need a lot of energy, right? So let's say that it only need 1 joule lah. Okay, this is the amount of energy. The number that I write inside the circle is the amount of energy that is needed. Okay, needed by the particle to oscillate at low frequency. So as the frequency increase, if you need to oscillate at higher frequency, of course it will need more energy lah. So let's say the energy it need is 2 joule. This one is 3, 4, 5, 6, 7, 8, 9, and 10 joule lah, for example. Okay, so at very high frequency, the particle, if want to oscillate at very high frequency, it need to absorb 10 joule. You need to get 10 joule energy, then only it can oscillate at very high frequency. Okay? So, I think I label lah. Okay? So this is amount of energy needed to oscillate. Okay? Okay, now the amount of energy that is transferred to an object is limited. Okay, is limited. So let's say that because the amount of energy that is transferred is limited, and all of the particles, oscillate at different frequency. That means, for example, you look at we look at this. Let's say we look at this oven heating element. You look at this oven heating element. Do all of the parts shine or glow at the same color? No, right or not? Some parts glow at the brighter color. Some is dark red color. Why like that? This means that different part or different particle oscillate at different frequency lah, right or not? Different particle oscillate at different frequency. Some particle oscillate at very high frequency. Some particle oscillate at low frequency. So particle that oscillate at low frequency will produce electromagnetic wave at a lower frequency lah. Okay, at a lower frequency. So remember, when a hot object, it will emit radiation in all wavelength. All wavelength also got. That means from radio wave until very high frequency. From radio wave until X-ray, gamma ray. All also got. So you see the particle. Let's say this particle need a lot of energy, then only can oscillate at very high frequency. So, but the energy that is transferred to the object is limited. Do you think there will be a lot of particles that get a lot of energy? Definitely not, right or not? Definitely not. So that means particles that get a lot of energy, let's say only one, let's say only one particle. Let's say only one particle get 10 joule and can oscillate at very high frequency. So as the energy requirement to oscillate is lower, you see, as the frequency is lower, the particle don't need a lot of energy. If the particle don't need a lot of energy, then the number of particles that get less amount of energy increase. The number of particles that get less energy will be more. So for example, particle that get 9 joule, let's say this one that get 9 joule of energy is 2 particles. 2 particles get 9 joule and can oscillate at this frequency. And then this 8, the particle that get 8 joule, you have 3. This one 7 joule, you have 4 particles that get 7 joule. You have 5 particles that get 6 joule. 6 particles that get 5 joule, and so on. Like that. So that means the particle that get a little bit of energy is at the highest number. At the highest number. Get the idea? It's the same like if you think like let's say everybody in the class, in the class. So let's say if you just take candy and throw all around the place, and then you ask them to grab as much candy as possible. So I think most probably you will get is the people that get the most amount of candy is only very limited lah. Only a little bit of people get a high number of candy, but people that only get 1 or 2 candy, you have more people. You have more people get more number of candy. Like that. So average number of candy, you get more people lah. More people have or have an average number of MD like that. Okay, so same with all these particles that get energy, that absorb energy. Okay, so some particles they can get a lot of energy, but the number of particles that get a lot of energy is very little, and particles that get very little energy is a lot. Okay, okay, so what happened to the radiation intensity? You see, if the particle get 10 joule, then that means it will be able to emit 10 joule of energy lah, right or not? Okay, it absorb 10 joule. Okay, absorb 10 joule, so it can oscillate and emit 10 joule. So the radiation intensity is is 10. Okay, let's say it's like this, 10, 20, 30. Okay. Okay, so that means this particle that that means very high frequency. Okay, radiation that is very high frequency, there is only one particle that can emit 10 joule at very high frequency. So here the electromagnetic wave, the radiation that is at high frequency, only 10 joule. Next we look at the 9 joule. Okay, have two particles can emit at this frequency, at absorb 2 particles, absorb 9 joule and release at this frequency, lower frequency lah. Okay, so 9 times 2, 18 lah, around here lah. You see lah. And then this one, you got 3 particles that absorb 8 joule, 3 particles. So total 24. So around here lah. And then this one, 28. Okay, around here. This one, 6 is 30 lah. Okay, this one, also 30. Okay, this one, 28, 24, 18, and then 10. You see or not? You see the shape of the graph. Very high frequency, less energy. The one in the middle, a lot of energy. Okay, a lot of energy. Okay, that means most of the particle will get that means the particle that can oscillate at like a moderate frequency will have more particles can oscillate at moderate frequency. Particle that can oscillate at very high frequency is very limited. Particle that can oscillate at a very low frequency also limited. Okay, like that. Okay, you see the shape of the graph is like bell shape lah, right or not? Okay, it's like bell shape. So you see, how is it that the idea of Max Planck, where energy is discrete and energy is limited, can explain, explain the result of experiment. Okay, result of experiment that cannot be explained through classical theory. This is from classical theory. Classical physics. This is from quantum theory. Okay, from quantum theory. can explain exactly. So the result through mathematical means okay, Max Planck he calculate and predict the shape of the graph based on his idea where energy is discrete and energy is limited. He get exactly the same graph like the graph that they get by measuring the radiation that come out from hot object. Okay, like that.